Hi, and welcome to Module 3 of Applications in Engineering Mechanics. In today's module, we're going to define multi-force members. We're going to review two-force members from my earlier course, Introduction to Engineering Mechanics. And we're going to start to apply the 2D equilibrium equations that we reviewed in the previous module to solve structures that have two-force members and multi-force members. So those structures that have two-force members and at least one multi-force member are basically divided up into two categories. One is a frame. We call it a frame. It's a stationary structure to support loads. As an example, a frame might be something like this stepladder again. This is a 3D structure, but we're going to model it as 2D and look at the loads that are applied on that stepladder. Other examples of structures that include at least one multi-force member are called machines. These are structures that contain moving parts. As the example I showed earlier, a pair of pliers can be referred to as a machine. They're designed to transmit and alter the effect of forces, and they have the purpose of doing mechanical work. So structures that contain at least one multi-force member also can contain two-force members. The multi-force members are defined as members that are subjected to more than two forces, and I'm going to show some pictures of those later on in the module. And they also contain two-force members, and you should already know about two-force members because we covered that in my Introduction to Engineering Mechanics course. And let's go back and look at that earlier course. So a two-force member is a weightless member, again, two frictionless pins. It can only be in tension or compression. And so in this case, it's going to be in compression. It's acting down at the top and up at the bottom. Two-force members could also be in tension, but that's all they can be. Those equilibrium required that the forces had to be equal to each other. They have to be in opposite directions, and they have to be collinear. They have to be along the same line of action. And so we found that By was equal to dy. They were equal. They were in opposite directions for equilibrium, and they're collinear. And shape is not a factor. And so I've got several examples. This could be an example of the hydraulic arm BD. And so if I have a compression at the top and a compression at the bottom, they can only act opposite each other. And no matter what way I turn, the line of action between those forces always stays the same. Even if it was in tension, you can see that the force at the top and the force at the bottom are equal, opposite, and along the same line of action. And so that's what a two-force member is all about. Shape's not a factor. So even if I take a curved two-force member like this, it can either be in compression at the ends or in tension, okay, along the same line of action. And just to show that shape isn't a factor, I've even took a weird S shape. And again, either in tension or compression. So if I drew that S shape, remember, it could be any shape at all. If I have two frictionless pins, one on this side and one on this side, the only thing this can be is in tension, like this, along the line of action, the line of action being the same for both of those forces, or it would be in compression. And here's the 2 points, and the forces could be in compression, equal, opposite, and collinear. Okay, so that should give you a good understanding of two-force members. When you can identify two-force members, you can get rid of all but two reactions. So that was a review of two-force members from my earlier courses. Now let's talk about multi-force members. Multi-force members are members subjected to more than two forces. So here's a couple of examples. Perhaps I have like a two-force member, two forces on the ends, but maybe I have another force here acting in the middle. Or perhaps instead of forces, I may actually have a moment or a couple acting on the member as well. So those would be multi-force members. They don't have to be straight. In fact, with the two-force members, I showed some S shapes, so maybe we'll take an S shape here again. It can be any shape you'd like. And let's say we have several types of forces acting and different moments couples. And you'll see examples of these in real-world structures. You'll even get a worksheet to do some of these later in this module. Okay, now we're going to apply the 2D equilibrium equations to solve these frame and machine structures, and we're going to apply this principle. If a body is in equilibrium, the entire body itself, each of its parts are also in equilibrium in their own right. So for my stepladder, for example, the entire stepladder and each part of the stepladder has to be in static equilibrium. And you'll see how this works as we go through problems. Now, this principle is actually quoted from a book by McGill and King. Dave McGill and Wilton King are actually colleagues of mine. They're professor emeritus from Georgia Tech. And this is the textbook I'll use several figures and examples from. Doctors King and McGill were kind enough to give me permission to use this text for examples. As I mentioned in my introduction to this course and in the syllabus, there is no required textbook for the course, but it's good to have an engineering statics book to use as a reference and for additional practice problems. And this is a good course that you, this is a good textbook that you might want to look at. So thanks again to Doctors McGill and King. Okay, let's conclude the module by doing a worksheet where we identify multi-force members and two-force members in the structures that are shown here. First of all, let's look at this structure on the left. You can see up here at point B that we have what we'll idealize as a frictionless pin. Here's an example of a frictionless pin. It allows rotation, but it doesn't allow any movement in two orthogonal directions, for instance, the X or Y direction. So that's a frictionless pin at B. You'll see that at point A down here, we have a rough surface or a friction surface. So A can't slide back and forth to the left or right. And so that also serves the same purpose as a frictionless pin because it allows rotation, but it doesn't allow movement in other orthogonal directions. And so we're going to say that point A serves like a frictionless pin. And knowing that, we now have AB with two frictionless pins as being a two-force member. But body BC now will have forces from the pin at B, forces from the pin at C, and a force here in the middle, so this will be a multi-force member. So let's do one more example together, and then I'm going to let you do the last two examples by yourself. In this structure, here's a bar with two frictionless pins only, so that is going to be a two-force member. This also will be a two-force member, BC. Are there any other ones? Yes, I see one down here. EF also has forces applied at just two frictionless pins. And that leaves two bars left. We have ADFH. That's obviously going to be a multi-force member because it has forces at A, D, F, and H. And B, C, D, E, G, not B, C, but C, D, E, G also has forces at several places. So those are both multi-force members. And I would like you to do the same sort of analysis on these other two structures. And I've included a solution to this worksheet in the module so you can check yourself out. So that's it for today's module, and we'll see you next time.